Hello, everybody. Welcome back. We are having our last lecture before the quiz that will be on Monday. I already included the topics for the quiz on e-class and what parts of the book and what notes and what problems to check. Uh, on Monday, we'll see um, heat transfer with phase changes. And then Wednesday and Friday, we're gonna see radiation. That is the main topic of your second assignment. So let's go through heat exchangers. So we already talked about the different types of heat exchangers. Here we have a concentric tube heat exchanger over which we will do an example today. And we saw the different types of heat exchangers. Oh, let me get the chat here. We saw the different types of heat exchangers like shell and tube, whether we have one shell and two passes or two shell and four passes, or some multiple of four passes, that eventually these configurations not only have implications from the point of view of cost and footprint on the plant, but also from the point of view of the calculations, there are particular correction factors associated with this. We saw fin heat exchanger, parallel plate heat exchangers. Here we have a schematic of the type of flow. In this case, the flow would go through a rectangular narrow cross section. Please look in past exams for concrete worked out exams by me of how to calculate this type of heat exchangers. You already know everything you need to know. The catch is putting it all together. So the challenge is not learning more, but about putting these things together. These type of heat exchangers, the parallel plate, they are parallel flow, so they are counterflow. And the interesting thing, if it is counterflow, the correction factor we discussed last time is 1. So this very complex looking heat exchanger is actually easier to calculate than a one shell, two passes heat exchanger. We saw parallel flow, we saw counterflow, we saw cross flow that is mixed, cross flow that is unmixed. And again, the reason for this is not only to distinguish different types of designs for which we would pay different money and would occupy different amounts of floor space in a facility, but also each of these different configurations have ways of calculating them. For example, when we looked at these definitions, we saw that there are correction factors. And these correction factors, they come from an analysis that is not too difficult, but it's an analysis we don't want to do here. We are only going to use the results. And the main challenge in using these graphs is in making sure that big T is not confused with big T, small t is not confused with big T, and O's are not confused with I's. When we have a heat exchanger that is very complicated, we assume that is a counterflow heat exchanger. And then and it's not, this is not a counterflow heat exchanger, but we assume it's a counterflow heat exchanger, and we would calculate a delta T log min for the counterflow heat exchanger. And then we would calculate here. And there we would calculate the correction factor using this graph, which we have for one shell, two passes, for two shell, four passes. We have for unmixed cross flow, for mixed cross flow. And what we saw last class too is that there are 3 key equations in the calculation of heat exchanger. We discussed 2. Equation number 1 was the equation of duty, and that has no changes what we have seen on week 1 of classes. So after the first week of classes, you were 1/3 of the way to understanding heat exchangers. I'd say this is a pretty good class. Then the second equation was the size of the heat exchanger. The size is given by the area of heat exchange. And we wrote an equation that is very much the equation we wrote on week 5 of class, right? That the rate of heat transfer is given by the overall heat transfer coefficient, the area, and the delta T. The delta T is a temperature difference between the hot and cold fluid. Here comes a twist, which we have also seen when we studied internal flows, but we are getting into more detail now. Delta T is not trivial because as the hot and the cold fluid flow through the heat exchanger, the hot fluid cools down, the cold fluid heats up. The temperature difference might not be constant. In the case of a parallel flow heat exchanger, the temperature difference between the two fluids gets smaller and smaller and smaller. So what do we choose for delta T, given that delta T is not constant? What we choose is the delta T log mean, which we have already discussed in internal flows. And here's the formula for delta T log mean. With this formula, we can calculate parallel flow heat exchangers, counterflow heat exchangers, condensers, and boilers. However, if we have a heat exchanger that is one shell and two passes, one pass of the tubes goes counterflow and the other goes parallel flow. What do we use then? What we use is the correction factor I just showed you before in the slides. This correction factor F, that comes from these graphs here. This is the value of F. So now this is the second equation, which we discussed on Wednesday. And we can now calculate the heat rate, or we got given that we know the duty from our first calculation, and from an understanding of the geometry of the heat exchanger, we can calculate an overall heat transfer coefficient. This delta T that is typically given by the design. You know the temperature of the fluids are coming in, and you know what temperature at least one of the fluids has to come out. For example, if we need to cool down oil, right? So from here we can solve the area. Let's go to the third equation then. And the third equation is, okay, let's pay attention to this overall heat transfer coefficient, which you saw already on week 5 of classes. And the overall heat transfer coefficient, you're going to recognize very quickly this equivalent electric circuit for heat transfer through the membrane that separates the two fluids. Can be a pipe, can be a plate, and we don't really care what it is. Can be circular, can be other things. We know how to calculate all those because of our unit on internal flows. So let's say, for the sake of an example, that we have a pipe, and this is a part of the cross section of this pipe. And here we have the wall of the pipe. We have on the inside, let's say we have some amount of fouling. Why not? Can be zero fouling, but if it's not zero, we know how to account for it. On the outside, we have also potentially another amount of fouling. And then we have a fluid, let's say inside. For the sake of this example, inside is the hot fluid and outside is the cold fluid. H and C are going to be the subscripts describing the hot or cold fluid, or I and O, whether it's the Well, that was inlet and outlet. So that's why we don't use inside and outside as we used before. I need to revisit that notation. So what was the equivalent circuit here? Let's start with the wall. The wall that we typically want it to be very highly conductive, because in a heat exchanger, we want fast exchange of heat. That's very much the opposite of insulation, like a jacket or a fridge. You want very slow heat, right? In this case, you would want the wall to be highly conductive, to be thin, right? To be made of a material that is good conductor. And here we have the resistance of conduction. Right next to it, to the right and to the left, we have the potential fouling, which I decided to include here. So we would have the thermal resistance of fouling on the cold fluid that is outside, or the hot fluid that is inside. In this case, because the heat would go through from one liquid through some fouling, then through the wall, then through the other fouling to the other liquid, we have a series circuit. Then we would have between this fouling and the fluid, we're going to have a thermal resistance of convection. And we marked it here. Resistance of convection here, and resistance of convection. Oh, I put cond, but this is convection. This is resistance of convection on the side of the cold fluid. And you might remember, these batteries here indicate the mean temperature of the hot fluid, in this case is inside, and the mean temperature of the cold fluid that is outside. If we're using oil or water, there's going to be no radiation. But if there is air, there's not going to be radiation either. And the reason is that for a heat exchange by radiation, we need two surfaces at different temperatures. And for example, if we have a pipe, we're assuming that all the inside of the pipe is at the same temperature, so there is no radiation inside. Similarly, if the pipe is outside looking out, typically it's looking at things of the same temperature. So typically, but not always, we forget radiation in heat exchangers. There are cases in which they work. For example, I know that in national labs, when they are playing with dangerous materials and they are doing very crazy experiments, they have heat exchangers based on radiation, in which they have something called a successor of graphite, in which something that is very hot radiates to the graphite and the graphite radiates it to the outside, right? We will not be worrying about those in this class, but know that if you needed to design things for nuclear power plants or nuclear experiments, you're ready to do it with what you have, plus the radiation you're going to learn next week. This is very powerful. You can do pretty much everything known to humanity right now. And the few things you might not know are things that would be tabulated. There's almost nothing that is a concept that you have not gotten from this class. Okay, so the total resistance, the total thermal resistance of this heat exchange through the wall of a pipe that accounts for potential fouling would be the resistance of the convection in the hot fluid, that is the fouling on the hot fluid, the conduction through the wall, fouling through the outside of the pipe on the cold fluid, and resistance, thermal resistance of convection outside. Let's see what these are. All these things you know is just a refresher. What is the resistance of convection? Was 1 over HA, the convection coefficient, and the area. Look at these, two things to notice. One, I'm putting convection coefficient in the hot fluid and area of the hot fluid. If the pipe is thick, the area inside the pipe is quite smaller than the area outside the pipe. We can account for that. We don't need to assume anything. These formulas, these concepts we're learning can accommodate for everything. They're super powerful. Now, let me tell you, all too often, the pipe has a thin section, and you just take the average diameter, and the area inside and outside are more or less the same. We're cutting corners. That's a smart corner to cut when it's true. But we cut corners only because we know how to do the things perfect. And then we decide to make our life simpler. Other thing, other than the area for hot and cold, is you see that this is an H bar. That means an average convection coefficient. This is not a local convection coefficient. Of course, if we go super fancy, we can start playing with local convection coefficients that we don't need, and we seldom do in heat exchangers. So we're looking here for average convection coefficients. If our pipes are working on the entry section, right, we would look at the average over the entry length, not at the local values. Let's talk about the conduction, right? We talked about convection. Let's talk about skip fouling for a second, and let's talk about conduction. If the right way of considering conduction through a pipe is with this formula, which we did see on week, that was week 6 of class, right? With this log here. All these formulas are in the formula sheet I already prepared. They're in the book, they're in the notes, right? Things over which you have already been tested. And as a group, you have tested awesomely on this. Now, it might not be a cylinder, it might be something else. For example, in the case of a plate heat exchanger, such as this, the cross-section of the fluid is not any longer a tube, but instead is a small square. Sorry, it's a very thin rectangle. A very thin rectangle, as these cold or hot fluid go, they go through a very thin rectangular cross-section. Okay. The heat by conduction would be just through the plate, is heat conduction through a wall. All things we already know. I will not be able to do examples for everything. I will do one example today, but you have in your notes many worked out by me. You can check. So let's talk about fouling, right? In fouling, the resistance for fouling is this R double prime, what we call the resistance per unit area, with the awareness that it's a horrible name because it's not per unit area, right? It's times unit area. So we need to divide by the area of the hot. We have already seen this. Trick here is not to get confused. So total resistance is R double prime divided by area. And R double prime, I'm giving you some tabulated values here from the book. It's a whole field of specialization, depending on what fluids you have, depending on what contaminants you have, depending on what type of operation you have, you're going to have different values of fouling. And also, this book is giving you typical values of fouling, but they're missing something. They're missing a time component. The day you bought the heat exchanger, fouling is 0. That I know. The day you reach this amount of fouling is long after you bought the heat exchanger. Say halfway in time between the day you bought it and the day you have this amount of fouling, you might have half the fouling. So the amount of fouling depends on time, not necessarily in a linear way, but depends on time. And based on these calculations we're doing, we should be able to predict the maintenance schedule of a heat exchanger by knowing how the performance of the heat exchanger is degraded as fouling is increasing. With these calculations, which we're going to do a sample today, extremely powerful. You can have a startup based on these things we're learning, because for the most part, people don't anticipate maintenance periods for heat exchangers. They just see when it's kind of sucks and then they deal with it. We can do so much. We could also assess the performance of antifoulants, right? In this class, we're going to focus on the heat transfer aspect of things. The practical aspects of design and operation, those belong in your design class that comes next year, but you'll be so ready for it. Okay, something in which we did discuss fins, and that was part of your assignment 1. If the tubes are finned, there are formulas for it. These formulas you can derive, but we will not. They are all derived in the textbook in the extended surfaces section. I'm not too keen because I see them as a particular case, but I want to use the results from these derivations for finned areas. And if you have a finned tube, the resistance of convection with fins is given by this formula. Let's look at it. 1 over H bar A. This looks very much like 1 over H bar A for resistance of convection, as we have done a million times. Where is the subtlety? A means the whole area of the pipe, and praying that my computer doesn't crash, I'm gonna take a chance here. So let's say this is the cross-section of a finned area. Let's see. Okay. Okay, so let's say that's the cross-section of the fin area, and this part here that I'm marking is all the metal, the material of the fins. One good thing coming out of this class is I think I'm buying an iPad finally. I was resisting it, but I think these drawings don't quite cut it. So what is the area? The area is this I'm going to mark here. This area marked here is the total area of the fins I'm marking in red. This here is the area we have. Now, because you did assignment 1, you know that the fin is hotter at the base and colder at the tip. So a long fin doesn't transfer, eventually the tip of the fin doesn't transfer so much heat because it eventually has more or less the same temperature of the outer fluid. So a fin has an efficiency less than 100%. And that is what is accounted in eta O. Eta naught, right? Is the efficiency of a fin array, of many fins. And how do I calculate the efficiency of a fin array? With this other formula here, that is also derived in the textbook, and this equation is 11.3 if you want to go check it out, and is based on the efficiency of a single fin, the efficiency of a single fin. And is 1 minus AF over A. A, we know what it is this one here. Eta F is the area of a fin that is tabulated. And if you look at the formula sheet, we have all the tabulations for the fins. And AF is the area of one fin, which I'm going to indicate here. AF would be the area of one fin. So based on this, now we can use these formulas and the tabulated values of fin efficiency to calculate a ridiculously complex heat exchanger such as, where do we have it? Such as this one here. Doesn't it look crazy? Looks crazy. But we know now what to do. And we have everything tabulated to do it, right? You see all these are so many that are the fins. But we would just calculate it based on the size of the fin. And we would have its area that way. So what would be the overall heat transfer coefficient? That was our third master equation, 1 over UA, and this A is the reference area. If you remember, the reference area is arbitrary. Can be that of the hot fluid, the cold fluid, inside, outside, whatever we want, but we must be consistent. We can pick anything we want, but we have to stick to it. So I'm putting it here, 1 over UA, this is area of reference, and would be you can do it. This formula is if the overall heat transfer coefficient is based on that of the cold fluid, or if the overall heat transfer coefficient is based on the hot fluid. Same thing, no problem. This is area of the cold fluid, area of the hot fluid, and is 1 over, this is the convection part. Let's consider no fouling first. The convection part, 1 over HA for the cold, 1 over HA for the hot, and the resistance of conduction in between. We knew it. Let's say we account for fouling. Same thing as before. And let's say we account for fouling and we have fins. The equation is so much the same as before, except that the convection part now has the overall heat the overall efficiency for the fins eta naught. See, these two terms look much the same. The only difference is this eta naught, and the same for the hot fluid. So this calculation here would be the calculation, going back, of this heat exchanger if it was fouled. Yeah, looks impossible, doesn't it? But we as engineers would know how to parse the problem and be systematic step by step and do what seems impossible, which is very possible and even easy, because somebody has done all these PhDs that you guys have not done, at least yet, and you're just using their formulas. 4 years each of sweat and tears for each formula you use. Okay, and here if we were to have fouling, here we have fouling on top of the fins if we were to have fins. Of course, for example, the heat exchanger I showed would not have fouling outside because air doesn't cause significant fouling. Could cause corrosion if it is air from near the sea, right? And in that case, if we have no fins, eta naught is 1. If we have no fins, is what we have known. Here we have the R double prime of fouling. That can be what we saw in that table. and in the table of representative foulings, although this is good just for this class, real fouling factors depend on time, and their books, they're specialists on that. In the case, we have an unfinned tubular heat exchanger, or for example, shell and tube, right? In which one of the fluids goes through a tube. This would be the formula. No more eta naught, because we have no fins. We said it's unfinned in this case. We can have fouling inside and outside. If it is a circular tube, we know how to calculate it. And this would be the formula. I included them here just to discuss them with you and you see what they look like. But really, we already knew this. We already did overall heat transfer coefficient under many circumstances. And the only new thing I brought up here is how you account for a system of fins using this eta naught. Let's do an example then. So let's calculate this is example from the book. So in addition of what you see here and what you can see if you watch the recorded video again, you can also go to the book and go step by step. But this is a counterflow concentric tube heat exchanger. The first example I showed, that is not a very common one, but they are commercial and it's easy to calculate in this case. So let's start with this. Past exams have more difficult heat exchangers. Your assignment has a more difficult heat exchanger. So please take a look at those. So counterflow concentric tube heat exchanger is cooling down lubricating oil. It gives you the rate of cooling water, right? Which is related to the pumps and the pressure losses. I will not deal with pressure losses in this class because we have our hands full with heat transfer. Pressure losses are something that relates to fluid mechanics. Now, when you have your design class, you'll have to deal with both, the heat transfer and the pressure losses. And you can design an amazing heat transfer, but if there is no pump that can pump through it, then there is no point. You'll have to use both. Here we worry only about heat transfer, and we take these flows related to pressure losses as given by the god of fluid dynamics that is in another church right now. So here we have the flow, in addition to a flow of water, we have the flow of oil. And we have the diameter of the inner cylinder and the diameter of the outer cylinder. So the oil comes in at 100 degrees and the water comes in at 30 degrees. We want the whole point of this heat exchanger, and the only point it would have, is to take the oil from 100 degrees C to 60 degrees C. And to do that, I have on hand water at 30 degrees C. So here's a schematic. It's counterflow, so it's gonna be easy. And this schematic is very clear. This is positioned in the heat exchanger. That being counterflow is very simple. Here we have the hot fluid that I don't need to tell you what it is because it's obvious. And we know that the hot fluid cools down, so the flow can only go from left to right. This arrow here is not necessary. We put it to be more clear, but if we don't put it, there's no choice. Things go from hot to cold, not the other way around. Because it's counterflow, the cold fluid goes from right to left. And by the way, I didn't need to tell you, looking at this graph, that this is counterflow, because the cold fluid is going always from cold to hot, no other choice. That means it has to go from right to left. Based on this graph, we can know the direction of flows, which one is each flow, the direction of the flows, and the type of heat exchanger. So these graphs look so simple, but they speak. Here is our oil that comes at 100 degrees C. This is our process fluid, and we want it at 60 degrees C. We know we have water at 30 degrees C. And in this case, they're giving us the flow rates. Typically, a flow rate of oil, we wouldn't control because it's part of the process. The flow rate of water, we would choose based on acceptable pressure losses. In this case, it's given. So we know 1, 2, 3 temperatures. We don't know this one, right? And they give us the properties for the fluids. And here we have a schematic of the cylinders. So what methodology we are going to follow? And this is pretty much every heat exchanger problem is a single problem for all classes in all the world. And is a problem in which we have to calculate the duty of the heat exchanger, which you already know. Then based on this knowledge of the duty, we can calculate the temperature we were missing, and with that temperature we were missing, we calculate the log mean temperature. In parallel, we calculate the overall heat transfer coefficient based on all these things we know. Practical handbooks of heat exchangers just tell you ballpark values depending on the design of a heat exchanger. Very often you might end up using that. However, in this class, we're going to learn to calculate it. So we could generate the tables we need, even if the manufacturer does not give it to us. Or better, we could design a heat exchanger the way we like it, if we have a new idea. This is what I care the most. My hope is that at least some of you will be the people who design and invent what doesn't exist today. And I'm giving you all the tools. And many others of us will do by heat exchangers from a specification. But it is my dream. We'll keep inventing new things and being always at the forefront of technology. And with what you're learning here, you can. Okay, so we calculate the heat transfer coefficient. For that, we need to calculate the convection coefficients of hot and cold fluid, sometimes the conduction through the pipe, assessment of fouling. And then we determine the heat exchanger size. And then, thank you very much. When you do your design class, you're going to learn that the heat exchanger size, there are tables that tell you what the price would be. So you would know the price of your heat exchanger and decide, is it worth your money to cool this oil this way? So, okay, let's, here we have our heat exchanger. Let's do step 1. Let's calculate the duty, which you know how to do. So it's easy. Duty is mass flow times specific heat. And we know for the oil that is the hot fluid, temperature hot minus the inlet minus temperature of the hot fluid at the outlet. And here we're assuming there is no phase change. Here we're assuming that the specific heat is constant. It's true that there is no phase change, but the specific heat is really not constant. So we get averages. In this case, I gave you, the book gives us a value. But if not, we go to the tables and we pick an intermediate temperature. From here, we get that the duty of this heat exchanger is 8,500 watts. Whatever it is, right? But that gives us already a size of the amount of power that needs to be exchanged. Based on this, we can calculate the temperature we were missing. You already know how to do this, but you will be doing this on Monday. You will be doing this. So you calculate the thing we didn't know, that is the outlet temperature of the service fluid, that is the water. And we have these expressions, which we had already seen. And we see that the water that was coming in at 30 degrees C is coming out at 40.2 degrees C. All these make sense. If all of a sudden the water was more than 100 degrees, we need to start worrying because we would have a phase change. But in this case, the oil is coming at 100 degrees, so I know the water is not going to be changing phase because it's not going to be going above 100 degrees. So let's calculate the delta T log mean. That would be delta T2 minus delta T1 over delta T2 over delta T1. What are delta T2 and delta T1? So we choose, so we have, so let's say this is, let me double check. Let's say this is delta T1 here on the right. Oh, here we put it. Delta T1 is here on the right, and delta T2 is here on the left. You can call them 1 and 2 and flip them, is all the same, but we stick with it. So delta T1 would be 60 minus 30. Delta T2 is going to be 100 minus what we just calculated, that was 40 point something. And this is what we see. Delta T2 is 100 minus 40.2. Delta T1 is 60 minus 30. Based on this, we calculated delta T log mean of 43.2 degrees C. And this delta T log mean of 43.2 degrees C is something kind of intermediate, right? Here we have 30 degrees. Here we have something like 60 degrees. And 43, what was it? 43 something degrees is some sort of a smart average, right? Based on the understanding of the exponential behavior of temperature. Now we got delta T log mean. Good news. Because it's a counterflow heat exchanger, F, the correction factor, equals 1. This problem was very simple. And for the time we have, I'm glad. We have problems in which F is not 1 that are all uploaded, solved by me step by step. Please take a look at it. Step 3, calculate the overall heat transfer coefficient. Look at this. They didn't tell us the thickness of the tube. Chances are I will. But in this case, they don't. If they don't give us the thickness of the tube, you know what you do? You assume what you like. Let's assume that the tube has essentially 0 thickness, as it has no resistance to conduction. Is true? No, it's not true. But it's almost true. That's the way you want in heat exchangers. And given that we have no information, there's no point in fretting over that. So we are not accounting for the conduction through the tube, through these two. Another thing, they said nothing about fouling. So happy, we are not going to account for fouling. If there is fouling, I will tell you. Or when you're in your professional life, you will know all too well if there is fouling or not. So in this case, the overall heat transfer coefficient, 1 over U is what we care about. 1 over UA is 1 over HA on the cold side plus 1 over HA on the hot side. So here we have an expression, but we need to know what the convection coefficient for the cold side is and what the convection coefficient for the hot side is. So let's start with the water. The water is flowing through the pipe. So this is an internal flow through a tube, easy peasy. Step number 1 for internal convection, check the Reynolds number. And we check the Reynolds number and we have everything we needed for it. And we get 14,000 something. The critical Reynolds number for turbulence was 2,300. This is turbulent. And guess what? This is awesome because that's what you want in heat exchangers, high heat exchange, high rate of heat exchange. If it is turbulent, we have the formula. That was this Dietrich-Belter equation. In this case, the water is heating up, so we use an exponent of 0.4. You know all this, and here's exponent of 0.4 and gives us a Nusselt of 90. The only thing that matters here is that Nusselt is much bigger than 1, as it should. And based on that, we can unpack it and get the convection coefficient, and it's 2250. If you remember, for liquids, forced convection in liquids, we typically would say 1000. Now we calculated right, we calculated properly, and it's 2250, right? We were not that bad for making it up out of thin air. This is the right thing, and this is the right ballpark. This is the number you use, right? Let's calculate the convection coefficient for oil. Same thing, it's an internal flow, but in this case now, it's a trick internal flow because it's annular, it's inside a ring. So we have to use the hydraulic diameter. I have to use this expression for hydraulic diameter, that is 4 times cross-sectional area of the annulus over the wet perimeter. The perimeter is all this perimeter, pi times diameter here and pi times diameter here, because it's wet on the inside and the outside. And the end result in this case is that the hydraulic diameter is outer diameter minus internal diameter, minus inner diameter. You can check it yourself. But if you do that, it reduces to this. When I put all of this here, we end up that the Reynolds number for the oil in the annular flow is 56, way below 2300 laminar flow. But what can I do? This oil is so ridiculously viscous that it's very difficult to make it turbulent. We're off by like almost by more than an order. We're off by more than 1 order of magnitude. By increasing the velocity, you're not going to transition it to turbulent unless the velocity is 10 times higher, and the pressure losses would be astronomical. So this is what it is. Do I like it? No, because I don't like laminar flows in my heat exchanger. I like turbulent flows, but I'm going to take it. So it's laminar flow, and we have fully developed laminar. That's something we're assuming that the problem doesn't say. We're assuming fully developed flow, but we should check for entry length. We're not doing it in this problem here. And if you have to, I'm going to ask you. So it says, depending on the ratio of diameters, what the Nusselt number we should have. In this case, we care about the Nusselt number on the inside between these two fluids. So the ratio of diameters is more or less 0.56. So let's call it 0.5. We can do extrapolation, interpolation, and I put that in the notes too. But let's call it 0.5 as the book does. And if you do 0.5, we would get a Nusselt number of 5.74. Of 5.74, right? And if we have 5.74, we unpack it, and from there we get a convection coefficient H, that is 39.6. Is far less than the 1000 we use for water, right? But oils are so viscous that they're laminar and their heat transfer is not so good. Oils are also very bad heat conductors. So it sucks up, we suck it up, and this is what it is. Based on this, we can calculate the length of the heat exchanger. There is something, and we have run out of time, that I do want you to read on your own. You have to do this. We have not talked in this class, but I want you to read this section on heat capacity rates that will be in the exam on Monday, heat capacity rates, this section 3. Please read it. It's also in the book in which we talk about boilers and condensers. This is important, and I ran out of time. This section 4, do not worry about section 4, that is the calculation, the derivation of delta T log mean. I will not worry about that. Section 3, you have to read, and I will ask questions related to this, as I have done in previous years. Let's stop here, and I will be back at 2 for office hours for those who wish to join. Thank you very much.